In this presentation, we look at developing measurement concepts, which can be found in Chapter 18 of your text.
To begin this chapter, let's start by talking about the meaning and process of measuring. Suppose that you ask your students to measure an empty bucket, like the one that is on this screen. The first thing they would need to know is what about the bucket is being measured. Is it the height, the diameter, the surface area, volume, or weight? Once students determine or are told the attribute to be measured, they can then choose a unit that has the attribute associated with what is being measured. Technically, a measurement is a number that indicates a comparison between the attribute of the object being measured and the same attribute of a given unit of measure. So we know that length might be measured in inches or meters, and volume might be measured in liters, for instance. So the attribute and the unit of measure correspond. Measurement means that the attribute being measured is filled, covered, or matched with a unit of measure with the same exact attribute. It's vitally important that the skill of measuring is explicitly linked to the concept of measuring as a process of comparing attributes, using measuring units and using measuring instruments. Let's look at a couple of goals and their associated activities. You usually start by introducing comparisons, and the goal might be for students to understand the attribute that's being measured. And one type of instructional activity to achieve this goal would be to have your students make comparisons based on the attribute. For example, is this longer or shorter, heavier or lighter? You want to use direct comparisons whenever possible. And then you'd move to step 2, using physical models of measuring units. And the goal here might be to have students understand how filling, covering, matching, or making other comparisons of an attribute with measuring units produces a number called a measure. And you'll use physical models of measuring units to fill, cover, match, or make the desired comparison of the attribute with the unit. These are foundational and introductory activities into the topic of measurements. It's common in the primary grades to use non-standard units to measure length initially. And this is an important first step that we really should persist making even into the upper grades, and I'll tell you why, for the following reasons. It helps students to focus directly on the attribute being measured. Irregular shapes can be measured with square tiles or circle counters, for instance, and it provides a rationale for using standard units. Standard units have more meaning after students have experienced measuring with their own collection of non-standard units. And here are a couple examples of good non-standard units to use. Giant footsteps, measuring ropes, drinking straws, connecting cubes, paper clips. You want to have some that range in all different size, because if you're measuring the length of a room, lining up paper clips would not be an efficient use of time. So you want to use ones that are closer to the scale of the object that you're looking at, that would promote some precision when you're introducing non-standard units for measurement. On this slide, I present a couple of ideas for measuring using non-standard units. So you could have students lay on the ground and in pairs outline each other on some large roll of paper, and then you could give them straws and have them measure their outline. You could also do pieces of rope as well. For a teacher's desk, you could use Cuisenaire rods, maybe the orange rod, for instance, and you could have them first estimate how many rods they think the length of the desk will take up, or then after they could do the actual amount and compare their estimation with the actual amount. And the Cuisenaire rod is great because remember that every rod has a specific centimeter length, so they could really be very precise with it. And then they could use paper clips as well, maybe to do the perimeter around a textbook. You'll want your students to focus on some key things with measurement. A, are they getting the same answers as one another? B, what is important with measurement? Making sure that they line up their unit of measurement end to end and that they're not overlapping. The overlap is what can lead to some inconsistencies between responses between students. So that's an important aspect for you to stress. So once your students have had some sufficient experience with non-standard units and they have a foundation now why we really need standard units, then you can begin teaching them. Teaching standard units of measure can be organized around 3 broad goals. The first is gaining familiarity with the unit. The second is developing the ability to select an appropriate unit. And the third is acquiring knowledge of the relationship between units. 2 types of activities can help students develop familiarity with standard units. The first is comparisons that focus on a single unit, and the second is activities that develop benchmarks for single units or easy multiples of units. I think students enjoy and are specifically interested for length benchmarks that are found on our bodies. These become quite familiar over time, and they can be used in so many different situations. And you don't need any other tools except for maybe some measuring tape in the human body. Let's look at the example on the slide. This one has you using metric tape measure, and you're asked to find the measure of a foot, a stride, a handspan, width of a finger, neck, wrist, waist, floor to shoulder, all these different things. And you're asked to graph the data and see how they compare. And what's so interesting is that your students will probably find some interesting revelations. That total height is equivalent to 7 to 7.5 heads. So if they measured the length of their head, their overall height should be about 7 to 7.5 times as much. The length of their face is almost identical to the length of their hand. Now, if you have very young students, their hands might be much smaller than the size of their face. There are things that change as your students get older, and as they get older, you'll notice that's one thing that becomes more proportional. But the length of a foot is actually equal to the length of a forearm. In fact, try it out right now, and you'll see that that's true. Students really enjoy making these self-discoveries. The waist to neck ratio is 1 to 2. So that's a neat one to discover too through graphing. What that is saying is that your waist is twice the circumference of your neck on average. Also, the neck to wrist ratio is 1 to 2, meaning that the neck is twice the circumference of the wrist. So there's some really fascinating relationships between measurements of the body, and students can start to see those as benchmarks for things to reference and relate to as standard units, and they're fun to explore. So we just reviewed a neat activity for helping students achieve Goal 1, which is gaining familiarity with units. Goal 2 is the ability to select an appropriate unit. And choosing an appropriate unit means making decisions like, should the room be measured in inches or feet? And we already kind of introduced students to that with non-standard units when we needed them to select an appropriate item to measure something. So we would use paper clips to do the perimeter of a book versus a large footprint to do the length of a room. And now they're coming back at it in standard units. So some questions that you would want them to be able to answer. Should the concrete blocks be weighed in grams or kilograms? To cut a piece of molding, do I measure to the nearest inch? To determine how many 8-foot pieces of molding to buy, do I measure to the nearest foot? These are really important practical questions that you're going to want to review with your students, and you can let them come up with some as well. Knowing the size of the unit and the level of precision that is needed are what are most important to meeting and achieving this goal. The third goal is knowledge of the relationship between units, both metric and customary. Countries worldwide have passed laws stating that international commerce must use metric units. So, if U.S. students are going to be prepared for the global workplace, they have to be knowledgeable about and comfortable with metric units. Since students will still use customary units on a daily basis, they do need to be able to use that system as well. And the relationships between customary and metric units are conventions, and they are something that have to be told to students directly. They need to see the conversion factor between a meter and a foot. It's not something that you need them to discover. You just want to let them know what the conversion factor is, but give them plenty of opportunities to see the relationships by making those conversions when it's appropriate. But even before you do that, especially when you're introducing any of the measurements or any of the customary or metric units, you need to let your students have some experiences with common items and either measuring them so they can establish some benchmarks in their mind for what represents a meter, or what would represent 1 pound, or what would represent a gram. And you see, like, a door weighs generally 2 meters. A doorknob is about 1 meter from the floor. A sack of flour is 5 pounds. A paper clip is about a gram. Letting students have these discovery opportunities will help them to have a greater understanding of what each unit really represents. Once they've had these understandings or have developed this understanding, you could start to introduce the different prefixes in the metric system. So remember, you have 3 for your smaller units, deci, centi, and milli, and 3 for your larger units, deca, hecto, and kilo. But you'll want to do that after the students have a grasp of the structure of decimal notation. We've talked about measurement. We haven't talked about estimating too much. I think we may have hit it just a little bit, but measurement estimation is very important, and it's a process of using mental and visual information to measure without using measurement instruments. And that's why benchmarks are so important, because they do help students to estimate. There's several reasons for teaching estimation strategies. First, they help students focus on the attribute being measured in the measuring process. For instance, think about using playing cards and asking students to estimate the area of the cover of a book with those playing cards. This requires students to think about what area really is and how the units might be placed on the book cover and how to relate the two. Estimation also provides an intrinsic motivation for measurement activities. It's often interesting to see how close your estimate is to the actual, and students love a challenge like that. It also helps students to develop familiarity with units. For instance, if you estimate or ask your students to estimate the height of a door in meters before measuring, you must think about the size of a meter. And so the students are really becoming more in tune with what measurement physically represents. And another great reason for teaching estimation strategies, as I've already mentioned several times, is that you can use benchmarks to make an estimate to promote multiplicative reasoning. So benchmarks not just for the visual power of it, but it can promote multiplicative reasoning. How so? Well, let's say that you say to the students, the width of the building is about 1/4 the length of a football field. Well, the students might have to estimate, if they don't know off the top of their head, how long is a football field. And then they would realize, oh, it's 100 yards, so if it's about 1/4 of the length, the width of the building is 25 yards. There are all different strategies that you can help your students use when they are learning to estimate. And they're all depicted pretty well on the screen. The first is developing benchmarks. So let's say that you use the height of a student in your class as one of your benchmarks, and you use that height or even a drawing or cutout of that student to estimate the length of the room. You could also use chunking or subdivision. See how at the top of the classroom picture that is on the slide, they chunked according to open space on the wall, windows, and bulletin board to estimate the measure of the room. And the last, you could iterate units, count out single units physically or mentally. And so with that student, the cutout of the student on the floor, not only are we developing a benchmark, but then we're iterating and counting, and there's that multiplicative reasoning coming into play. There are a couple of teaching tips that I really want to stress, and some of them might be contrary to what you've encountered in the past. First, you need to accept a wide range of estimates. We're telling students to estimate, so it's not going to be exact. So you need to broaden the scope of what you're going to accept so that students don't feel that the overall goal is precision, but rather accuracy, so you need to broaden it a little bit. You don't want to promote a winning estimate because that can discourage students, and it really does put the emphasis on precision rather than just having a range. You want to make measurement estimation an ongoing activity so that you can promote long-term memory of it. And even though we don't want to accept precise estimates, we do want to be precise in our language. Do not use the word measure and estimate interchangeably. Measure means you want a precise value. Estimate means that you're going to accept a range of values. Okay, so far we've talked broadly about measurement. We've looked at the 3 major goals: gaining familiarity, choosing the right measurement, and then being able to examine relationships between different measurements and finding good benchmarks to help us mentally estimate measurement. But now we're going to look at some different specific types of measurement. We're going to start with length. Length is usually the first attribute that students learn to measure. It is found by locating 2 endpoints and examining how far it is between those 2 points. Length is not immediately understood by young students. There are some common misconceptions, like measuring from the wrong end of the ruler or beginning at 1 rather than 0. This has to be pointed out to students, and oftentimes it's really helpful if you can go from one student to the next to ensure that they're measuring correctly, or pair them up with a partner who has seemed to master the skill so that you can make sure that they're starting at 0. Another common mistake is counting the hash marks rather than the spaces. And another one is not aligning 2 objects when comparing them and not lining them up exactly from one end to the next. Students in pre-K and kindergarten should begin with direct comparison of 2 or more lengths and then move to indirect comparisons by 1st grade, but you want to start out very concrete, and when they're working with the ruler, make sure that you avoid them making these mistakes by individually working with them or having them in pairs where they can help one another develop these skills. I know I'd mentioned this generally at the beginning of this PowerPoint, but even with length and with all your units, you want to make sure that students' initial experiences are with non-standard units. So have students' first experiences with length be with something like giant footprints, or perhaps pieces of rope that are cut into 1-meter pieces, or drinking straws, or as we saw in a previous slide, paper clips or Cuisenaire rods. After they've had plenty of opportunities working with non-standard units, then move to the standard ruler or meter stick. You could even have students create their own rulers. The one on the slide is pretty precise insofar as students cut 1-inch squares out and then they numbered them, and they could then use those to measure. But actually creating it and then labeling it with numbers helps them to become more in tune with the numbers and the fact that it has to take up that entire interval or block of space to be that length. This actual exercise is in the book. It's labeled Activity 19.13, and it's on page 465, and there are some different alternatives to it as well for different grade levels, but it's a nice hands-on activity for students to become familiar with standard units in length. So we've talked about length. We're going to move to another type of measurement. We're going to move to area. Generally speaking, area is the measure of 2-dimensional space inside a region. Recent data actually suggests that 4th grade students do not have a complete understanding of area. Estimating and measuring area begins in 3rd grade, and it continues into grade 4 with finding area of rectangles using formulas and also by being exposed to some real-world problems. In 5th grade, students move to volume of 3D shapes, and then in 6th grade they'll explore surface area, and then 7th grade they start to explore circles. Comparing area measures is a bigger conceptual challenge than comparing length measures because areas come in a variety of shapes. It's not as direct as just comparing length of 2 objects. Comparison activities with areas should help students distinguish between size and shape, length, and other dimensions. For instance, look at the left side of the picture on the slide where you see the collection of quadrilaterals and triangles. all of these shapes have the same exact area, though they are in different shapes. But they all have the same two-dimensional space inside that region. And that's what students are going to start to discover as they start looking at area. Prior to students learning formulas, students are going to need multiple opportunities to cover the surface, because that's really what area is. It's how much material do I need to cover this surface of this two-dimensional shape. Squares, playing cards, two-color counters, index cards, post-it notes, these can all be used to fill up a 2D plane. And then you can move to models with standard units, maybe like Cuisenaire rods that are more exact. Really, though, your initial objective in the beginning is to develop the idea that area is measured by covering or tiling the surface of an object. Here's a great comparison activity building on the graphic that was on the previous slide. This is activity 19.15 called Two-Piece Shapes on page 467 of your eText. Here's what you want to do first. You want to cut a number of rectangles of the same area, about 3 by 5 inches. So you could really just use index cards for this. You want to have students work in pairs and give them 6 rectangles each and ask them to fold on the diagonal and make and cut 2 identical triangles. And then you're going to ask them to rearrange the triangles into different shapes, just like the ones that are on the screen here. And then you just want to have a class conversation where you discuss the area and the shape of each response. Does one shape have a greater area than the rest? And you want students to differentiate, that is, between shape and area so that they can have a good solid frame of reference for both of those and differentiate between the two in their minds moving forward. Here's another terrific comparative activity using physical models to explore area. Say you give 2 students 2 rectangles that are similar in size but different, and then give them several single square units. These can be cut out of construction paper, for instance, and you want to make sure they're all the same size that they can use to tile the entire rectangle with. This is a great activity because it allows students to begin connecting multiplication to area. They'll realize that one row can be established and simply multiplied instead of filling the entire rectangle. That first row begins to be thought of in their minds as a single unit that's simply replicated to fill the entire rectangle. And the back rectangle, like if you're using an index card, for instance, it really becomes like their area ruler or a grid so that they can lay all of their units out on so they can see the relationships that are occurring. So we've seen how students can deduce that they're going to be multiplying length times width in order to get the area of a rectangle. And they can deduce that when you give them several different concrete opportunities to explore that over and over. They start to see the multiplicative relationship. When students develop formulas, they gain conceptual understanding of the ideas and relationships involved, and they engage in doing mathematics. Overemphasis on formulas, especially right away, with little or no conceptual background, results in so many misconceptions. 2 major misconceptions are: 1, confusing linear and square units. Remember, area just isn't the length of 2 lines. Even though you're using those, you're finding the square units for the surface that can be covered inside. And the second misconception is difficulty in conceptualizing the meaning of height and base. You're going to want to show that any side of a polygon can be conceptualized as a base, and each base has a corresponding height. In fact, let's talk about rectangles, because I know that we've been taught, or you've been taught, that you want to find the area by multiplying length times width. But it actually is better, and I think you're going to notice this in the textbooks that you're going to use with your students, that we're trying to make a shift to saying base times height, because that's where they intersect perpendicularly, and the length of the base and height tell you how many square units, because they intersect at a right angle, how many square units fit on each side, and their product will tell you how many total. And all of the rest of the area formulas incorporate base and height instead of length and width, so it's a natural change to make. Once students understand the base times the height formula for rectangles, the next challenge is to determine the area of parallelograms. And here's going to be an activity that I would suggest that you do. Give students a parallelogram similar to the one that's on the grid on the left-hand side of your screen, and ask them to connect their understanding of a rectangle to it by decomposing it and reconfiguring it into a rectangle. What they will notice is that they can cut one of the triangles off at the end, move it to the other side, and they've now composed a rectangle whose area is base times height. So now they have the area of a parallelogram. After developing the formula for parallelograms, triangles naturally follow. Well, how so? Well, if students cut a parallelogram in half, they have two identical triangles. So a triangle would be the area of a parallelogram divided by 2, or 1/2 base times height. Lastly, you're going to want to move on to trapezoids, and this can seem a little daunting to students, but if you take a trapezoid, like the one that's on the bottom right of your screen, and you produce an identical one of it, but then you just rotate it, the two of them can be connected and form a parallelogram. Well, we know parallelograms area is base times height, but how do we figure out what our base is? If we label the two parallel sides of our trapezoid as base 1 and base 2, then the entire base of that new formed parallelogram would be base 1 plus base 2. You would take that sum and you would multiply it by the height to get the area of what? That entire parallelogram that you formed. But you don't want the area of the parallelogram, you want the area of half that. Half that forms that one trapezoid. So that would give you 1/2 times the height times in parentheses base 1 plus base 2. That seems a little complicated, but the students can come to an understanding of it, especially if you give them opportunity to explore with the shapes. Once they've explored it and they see how the equations can be justified, then you can encourage them to commit them to memory. What about the area of a circle? This is a little more tricky, and honestly I think it can be even more difficult to understand in a PowerPoint instead of demonstrating it in class. So if you need to pause this, please do so and take some time just to look through the figures that are on the right-hand side to see if it makes sense. But this is part of the Common Core State Standards. The students would be able to move from an understanding of the circumference formula to an evolution of the area formula in 7th grade. So it's something you want to be able to familiarize yourself with. Okay, so the best way to demonstrate the evolution of the area formula is to start with circumference. Now remember, circumference is simply distance or perimeter around the circle. If you took rope and you put it around a whole circle, then measure the length of that rope, or you just use measuring tape and measure the whole length of the circle. That's what circumference is. Now, let's say you start with the formula for circumference, which is 2 pi r. So you would give that to students. Okay, and you say the whole distance of this circle is 2 pi r. Let's cut it up into 8 wedges. Now we're going to take these 8 wedges, which are blue, and they're on the screen, and we are going to configure them like pieces of pizza to look like a near parallelogram. And then you want your students to think about what the length of the base and height are, or the measurements of the base and height. Well, they should realize that the height is the radius, and that makes absolute 100% sense based on the fact that the radius is the distance from the center to the outside of the circle and from the way you have it arranged. And then how about the base? Well, you have half of the wedges lined up at the top and half of them lined up at the bottom, so that should be half of the circumference. So instead of 2 pi r, just pi r. Well, if they have a near parallelogram, they could determine what the area would be. Area is base times height, which would become pi r squared. Now they might say this isn't an exact parallelogram, and you could say, well, let's cut our wedges even smaller. And if they did so and made 24 wedges, just like the yellow figure there, they would get even closer to it. But what they're going to realize is the measurements are the same. They still have a height that's equal to the radius, and half the wedges are along the top and half the wedges are along the bottom, so that they have pi r as their base. And so area again would be pi r times r, which is going to be pi r squared. Seeing this visual really helps students to understand where the area formula comes from. Volume and capacity are both terms for the measures of the size of three-dimensional regions. And this is a topic that's going to begin in 5th grade and continue into 6th to 8th grade. The term capacity really just refers to the amount that a container will hold. And understanding and gaining a scope for different capacities can really be effectively explored through hands-on comparison activities. So one activity that I would suggest doing is having a target container or a standard container that you set up and having students sort and say, does this container hold more, less, or the same as this other container? So they start to visually think about how much containers can hold. Let's talk about developing the actual formulas for volume as well. I think it would be good maybe to start with a gift box and deconstruct it to help students understand why you need 3 units to tell you how many cubes can fit into the shape. And what they might end up realizing, and you can even demonstrate it with a drawing like the clear rectangular solid in the red cubes, is that if you know the area of your base and you then can measure your height, you just multiply the area of the base times the height to determine how many cubes that you can fit in, because every row is going to be the same since it's a solid figure. And so that would explain why you have 3 different measures that are multiplied by each other. They then start to connect the fact that, oh, I have these 2 parallel bases, so if I just multiply the area of the base times the height, this should also then work for cylinders. But my base is now just 2 parallel circles, so I'll do the area of a circle times my height. What about coming up with the area for pyramids and cones? Well, you could let students kind of discover this on their own by bringing in relational geosolids. There are actual manipulatives that are fillable that look like a pyramid and a cone, and what they will realize is that they have to fill up a pyramid or a cone 3 times to fit into the rectangular solid or into the cylinder, and so they're able to establish that relationship on their own, and that's an exciting way for them to discover that. Oh, when you think about it, measurement is just such a vast concept. So we've looked at length, we've looked at area, we've looked at volume. Now we're going to go on to measuring angles. Understanding the concept of angles and measuring angles is one of the mathematical standards in the Common Core State Standards that begins in grade 4 and develops in middle school. Angle size is often misunderstood, and protractors are commonly introduced and used without students understanding how they work. The attribute of angle size might be called the spread of the angle's rays. And in math terms, angles are composed of 2 rays that are infinite in length with a common vertex. So a ray just extends infinitely in one direction, but they have one endpoint. And for an angle, the 2 endpoints meet together to form your vertex, and then obviously the other 2 ends extend indefinitely into infinity. To help students conceptualize the attribute of the spread of the rays, 2 angles can be directly compared by tracing one and placing it over the other so that they can see the more spread out these 2 rays are, the greater the degree measure of the angle. You want to be sure to have students compare angles with rays of different lengths, because the lengths of the rays do not affect the spread of the 2 angles, because they have to remember that these rays, even though they're not drawn on infinitely, do go on infinitely. A student may think a wide angle with short rays is smaller than a narrow angle with long rays, and so if you just provide them lots of examples, they can quickly discern that this isn't the case. It's important to teach students to line up their initial ray with 0 when you are introducing the protractor. A lot of times students will misuse the protractor and line it up with 180 degrees and then get the wrong measurement. So you just have to be really in tune to going around and checking the students and making sure they're starting with 0. And once they get that down, they usually have it down. It's also important to teach the benchmark angles and associate them visually so students can see what does 30 degrees, 45 degrees, 60 degrees, 90 degrees, 135 and 180 look like. Why are these benchmarks? Well, these are going to lead into right triangle trig for students in high school with your 30, 60, 90 degree angles, your 45, 45, 90. Why is 180? Because it's a straight line, and so much is based on that with complementary and supplementary angles as students move on. So it's very important they have a visual context for these angle measurements. Okay, we're going to move on from angle measurements to time. Time is different from most other attributes that are commonly measured in school because it cannot be seen or felt, and because it's more difficult for students to comprehend units of time and how those units are matched against a given time period or duration. Here are several suggestions for helping students focus on the actions and functions of the minute and hours hands. So you could begin with a one-handed clock, and you want to make sure you use appropriate language. It's about 7 o'clock, so just start out with the hour hand. You could discuss what happens to the big hand as the little hand goes from 1 hour to the next, so they can start to see the relationship between the two hands. You could use 2 clocks, one with an hour hand only and one with 2 hands, so that you can scaffold or move students to the 2-handed clock. You definitely want to teach time in 5-minute intervals. You want to point maybe to 4 and say it's about 20 minutes after the hour. That way they can start to see, okay, when I'm at 4, I've had 4 chunks of 5 minutes. Go on, talking about the minutes hand, of course. You definitely want to also introduce students to both an analog and a digital clock, and make sure that you can show students the comparison between 2 times, what 5 o'clock looks like on the analog versus on the digital, and then what 7:20 looks like on the analog versus the digital. You want to relate time after the hours to time before the next hour so that students can see how the hands are positioned in both of these. And then, of course, you'll need to discuss the issue of AM and PM. This is a lengthy task, but it really is so vital for students. Obviously, time is something that they're going to need to be well acquainted with for the rest of their lives. One area that is tricky for students is determining elapsed time, because even though time is linear, we have 2 sets of 12 numbers, and it's hard for them to make an AM to PM jump. And I'll tell you what, I didn't realize how difficult this was for students until I was teaching elapsed time in a pre-algebra class in high school during my first year of teaching. I asked the students how much time elapsed from 8:40 a.m. to 12:20 p.m. and the students just quickly subtracted and said, oh, it's 4 hours and 20 minutes. And I was kind of shocked that they said that. And the reason they do this, they treat it like it's normal subtraction. Well, how do you get them to move away from that? I would suggest giving them an empty number line and have them use each hour as a benchmark to count each segment of time. So if they're starting at 8:40, you would want them to just move to 9 and write the amount of time that's taken place, so that's 20 minutes. And then they could even take a whole leap from 9 to noon and realize, oh, that's 3 hours. So I'm at 3 hours, 20 minutes, and then go from noon to 12:20, that's another 20 minutes. So on the two bookends, they have these 20 minutes, so add those together. That'll give them 40 minutes total and 3 hours. So 3 hours and 40 minutes is the elapsed time. I think that the empty number line and counting in segments from your starting time to each preceding hour is a really effective way for students to be introduced to elapsed time. On the screen, you should see the same type of scenario indicated using the elapsed time from 10:45 to 3:30 as a model, but it's occurring in the same way that I described 8:40 a.m. to 12:20 p.m. The last type of unit that I want to talk about concerning measurement is money. And this slide contains a list of the money ideas and skills typically required in the primary grades. It goes from recognizing coins to solving word problems involving money. The names and values of each coin are something that students simply must be told because they are just conventions of our system. Students really must understand 5, 10, and 25 and think of these quantities without seeing countable objects, which can be a little confusing at first for students to recognize that a quarter really means 25 pennies, that a dime means 10 pennies, and that a nickel means 5 pennies, even though they're only seeing one item. Gaining a sense of what we call monetary value and different ways to produce equivalent values is something to stress in the early grades. So you'll want them to give them fake money and tell them to create $1 in 3 different ways so they can start to see that value is relative to the coins that they have available.